A waste is any unwanted, unusable, or discarded material resulting from human, industrial, or natural activities. Waste can be solid, liquid, or gas based on its physical state. Plus, it's either biodegradable or non-biodegradable based on its chemical makeup. From the exam point of view, let's break down waste by its source of generation. First, we have agricultural waste, which includes all those byproducts from farming. Then there's municipal solid waste, the everyday trash coming from our communities. Next is hazardous waste. These are the substances that are toxic, corrosive, flammable, or reactive. Example like chemical solvent or industrial acids. Next category is biomedical waste that comprises of infectious and hazardous waste produced by healthcare facilities. The last one is radioactive waste. For the effective waste management, we look at two main things: physical properties like density, moisture content, field capacity, and particle size, as well as the chemical properties that includes proximal analysis and ultimate analysis. So let's start with the first physical property: density. Density tells us how much mass fits in a volume, and hence its formula becomes mass divided by volume. It is expressed as kg per meter cube. Density plays a key role in choosing how to collect, transport, and store materials. Did you know that low-income countries like India have more waste density? That's because their trash has a lot of organic stuff, moisture, and dirt. In contrast, high-income countries produce less dense waste. Next property is moisture content. It's the weight of water compared to the total weight of solid waste. It is expressed in percentage. High moisture makes waste bad for incineration, but great for composting. Field capacity is the maximum amount of moisture the waste can hold against gravity. Once this capacity exceeds, the excess water drains downward to form leachate. This is a vital factor in landfill design. For example, it helps engineers in designing a proper bottom liners and drainage system for a landfill based on how much leachate it will be producing. The last physical property is particle size. Understanding the size of solid waste matters. For example, smaller pieces make it easier to compost, giving bacteria more to work with. However, very small particles can cause compaction and restrict the airflow. Next comes the chemical properties of waste. First, we have proximate analysis, which gives us a solid idea of how waste behaves chemically and its energy content. This analysis is heavily used in waste-to-energy planning. It breaks waste into 4 easy categories based on how they react when heated. First up is moisture content. It's the water weight lost at 105 degrees Celsius. Less moisture equals higher net calorific value. Next, we've got volatile matter. This is what vaporizes when heated rapidly in the absence of air. High volatile matter means quick burning, great for energy recovery. Next, there's fixed carbon. After burning off the volatile matter, we are left with the solid residue called fixed carbon. The waste that has high fixed carbon value is worth energy recovery. Last is ash content. It is the inorganic residue remaining after complete combustion of waste at high temperatures. During the proximate analysis, the gross calorific value of waste is calculated using the Benton equation, according to which gross calorific value is equal to 44.75 times volatile matter percentage plus 80 times fixed carbon. Ultimate analysis breaks down solid waste into its basic elements: carbon, hydrogen, nitrogen, sulfur, and oxygen. It provides the elemental composition of the waste that's crucial for calculating the precise amount of air required for combustion and assessing pollution potential. Instead of the Benton equation, ultimate analysis data uses Dulong's formula to find the gross calorific value. That was all. Stay tuned for more. Subscribe and thanks for watching.